What we were doing last time, which was solving exponential equations. Give me just a second, Okay, no. All right. So we were, at the very end, we had talked about exponential equations last time, right? And, exponential functions, and then towards the end we were trying to solve some equations. And so we're going to finish that up and we're going to start logarithmic equations. So take a look at this equation. Let's see if we can solve this thing for x. Kind of strange, huh? So when I look at something like this, the first thing I guess I realize is x is in the exponent, right? Not down in the base. That's different. So I initially try and see if I can look at these two bases as being like powers of one another or something. Like, I know that 8 times 2 is 16, right? But that's not what I'm looking for. What I'm looking for is see if 16 is a power of 8, which it is not, right? 8 to the first power is 8. 8 squared is 64. So these are not powers of, or this one is not a power of 8, right? But do you recognize something that they do have in common? That they're powers of something, right? 8 is what? 2. It's 2 to the third power, and 16 is 2 to the fourth power, right? So I have to see that first. So I'm going to rewrite 8 as 2 to the third, but then that is being raised to negative x plus 11. And then 16 I'm seeing is 2 to the fourth, but that's being raised to the 2x. So all I've done there is rewritten the 8 and the 16, right? That's it. Questions? So for each of those, now I'm going to use just a property of exponents that was back from early on in this class. I remember I wrote all the properties on the boards, those little rolling boards, had them right over here. If we have something to a power, what do we do to the powers? Multiply them, right? We multiply them. So I have 2 to the third to the negative x plus 11, so I'm going to multiply these two powers together. This becomes 2 to the 3 times negative x plus 11, and then this one becomes 2 to the 4 times 2x. There I don't need parentheses because I'm just going to multiply these together, and there's no distribution that needs to occur like over here. Y'all see that? Everyone got it? Okay, now distribute through. Distribute through, we get 2 raised to the negative 3x plus 33 equals 2 to the 8x. That's just multiplying 4 times 2x. And now we finally are at a point where we can say, all right, if this is 2, right, and this is 2, and the 2 on the left is being raised to this power, and the 2 on the right is being raised to that power, that means that these two have to be equal. In order to maintain the equality here, we have to set those two equal to one another. So we just set the exponents equal to one another. And now what we've done is we've reduced the problem to just solving a little linear equation. And so I just try and get x by itself. What do you think? Add 3x to both sides? Add 3x. We get 11x on the right. Divide by 11, we get 3. X is 3. What do you think? Is that all right? Y'all okay? Tired? Okay.
You see the car wreck that was on fire?
No, I got here really early today, so.
That was bad.
Was it just now? Really? Where was it? 1604?
It's literally like right
Huh.
here.
I didn't see it. Is that why y'all are so quiet?
It's been very recent.
Because of the car wreck? Well.
Was it the Kia?
Did you cause the accident? Did you cut them off?
Wait, what happened?
What did you do?
It was just on fire.
Mm-hmm. Sure it was.
Pulled over and then it was just on fire.
All right, I want to do another one of these. All right, I want to do another one of these. You pick one. Which one of those do you want? I just did 75.
80.
80? Yeah, I was thinking 80 looks pretty good. 80? 72 looks weird as well. Okay, let's do. I'll show you 72 real quick because 72 is not bad at all. 72, 5 to the x plus 3 equals 1/5, right? So watch, it's one step and I think you'll be there. You'll see it. I'm just going to rewrite this. Remember me talking about going to the deli and asking for, right? This is 5 to the -1, right? And now these bases are the same. Just make that equal to that and then you're done. Okay? Not so bad, right? So your answer is -4. Okay. All right, so that's that one. Okay, now 80. 9 to the 2x times 27 to the x squared equals 3 to the -1. See, they could have put 1/3 here, right? And that would have made it even a little more difficult if they would put 1/3, but that's what they gave us. All right, so I look at that and I'm like, holy crap, what do I do here? Well, I have to recognize that 9, 27, and 3 are all powers of 3, right? You're going to say that, okay. So first rewrite 9 as what? 3 squared, but then that's raised to the 2x. Times, now 27 is 3 cubed, and then that's to the x squared, and then equals, this is just 3 to the -1. So there, what I've done is I've just rewritten everything so that I have a base of 3 in all of them. And then I'm going to use that property that I just used a second ago. Multiply, multiply, right? So we should have 3 to what power? 4x times 3 to the 3x squared equals 3 to the -1, right? Okay, we got to be careful here because this problem is giving us something that we haven't seen in one of these yet. That's right, we got to put these together first, okay? So now I'm going to use this property. If I have x times y, right, sorry, let me write it this way. That's not at all the property I meant to write. X to the n times x to the m. Same base, different exponents, multiplication between, right? What do we do the exponents here? We add them, right? We add the exponents. So I have 3 to some power times 3 to some other power. This becomes 3 to the, add the powers, 4x plus 3x squared equals 3 to the -1. See that? Yes or no? You can see? So I've added the powers together. Now can I set the powers equal to each other? Yes. I can set this, right, equal to that. And when I do that, I get 4x plus 3x squared equals -1. And then this is a quadratic equation, right? That's a quadratic equation. So I want to go and solve this now. So to solve a quadratic equation, first thing I'm going to do is bring everything over to one side. And when I bring everything over to one side, I'm also bringing that -1 over. I'm also going to rearrange the order so that I'm in descending order, highest power of x down. And then I have the pleasure of either using the quadratic formula there or factoring using that thing that we did in the beginning of class to break this thing down. I'm just going to go right to it though. So this should become 3x, x, 1, 1 plus equals 0. So you can check for yourself, when you multiply this together, you get 3x squared, then you get 3x, then 1x, then 1. And so this does, in fact, work.
-1 and -10.
Yeah, so now you set each of these equal to 0. And you you get x is negative 1/3 and x is negative 1. We have two solutions. So that means if I plug negative 1/3 in here and negative 1/3 in here, this should be true. If I plug in negative 1, it should be true. Let's check. I'm normally not going to ask you to check, but just so that we feel good about ourselves that we actually did something here, let's check this one. I think this one will be easier to check. Let me take the original problem and replace all the x's with negative 1. All right, 9 to the negative 2, right? That's what that means. 27 to what power here? Negative 1 squared is 1. So this is just 27 to the 1. Does that equal 3 to the negative 1? Does it? Hold on.
Doesn't look like it, no.
What's wrong? What does this become? What is this really? You gotta be careful. It's not multiplication. What does a negative power mean? Remember the 1 over 9 squared. This is 27. Does that equal 3? Well, can I rewrite this as 1/3? See, it looks like it may not work, but just keep going. What's 9 squared? 81. So this is really 1 over 81 times 27. Does that equal 1/3? Yes, because you can reduce this fraction. It's 27 over 81. It's 1/3. So it works. That's just to show you that it worked. Okay. Questions? Now I want to remind you of something here, all right? See the problem here that we did, this one? If I change this 5 to a 7, it's over. Okay? It's over for us because over is not good. Okay? Because what happens is we could rewrite that as 7 to the negative 1, right? But now you're going to have a major problem because what we've been doing to make these things work is we've been able to rewrite all these problems so that they have the same base, right? Here, there's no way you're going to rewrite 5 or 7 to have the same base. No way, all right? So the question becomes, how do we solve this? Because, I mean, our math, we should be able to solve this still, right? And we do have a way of doing it, but it requires logarithms. So the problems right here, the reason I'm not I'm not going to say I'm not a fan of them, but it's not super important that we be able to do this is because we're going to learn a method that's going to be able to solve this and that without doing what we just did. So, you know, I think it's better to have a method that works all the time than a method that only works sometimes, right? This method only works when you can get the same bases, which in the real world, that doesn't happen very often. All right, we ready to get into logarithms? Yep, okay, great. So to start logarithms out, and this is 6.4. Hold on. Where's my calendar? I just had the calendar up. What the heck? Yeah, 6.4. All right, I'm going to be showing notes over there, but just remember you can get to all these notes, right? And I'll just kind of point to that when I need it. 6.4 is called logarithmic functions. Logarithmic. Logarithmic functions. Okay, let's start with something. Recall. If I give you f of x equals 3x plus 4, how do you find the inverse. Let's see if y'all remember how we find the inverse of a function. There was a set of steps.
It's y.
Okay, first change the f of x to y, right? So the first thing I do is I switch this over. I say, okay, y equals 3x plus 4. By the way, we only look for an inverse function if this function is 1-to-1, right? Remember 1-to-1 has to be 1-to-1 in order. So this is a line, and is a line 1-to-1? Yes, it can pass the vertical and horizontal line test. So this is a 1-to-1 function, so it has an inverse. First thing we do is we change the f of x to y, then what?
You switch to y.
Everywhere you see y, put x. Everywhere you see x, put y. So x here, y there. And now, last step, solve for y. Get y by itself. So I'd subtract 4 on both sides. And then I'd divide both sides by 3. And that's y, right? And so that means my inverse function is x minus 4 over 3. Okay, we've done this, yes? Does it look familiar? Do you remember what the graph, right? What the graph of this and its inverse looks like when you put them together on the same graph? A mirror image over what, though?
Over 45 degrees.
Over that like 45-degree diagonal line, which we call the identity. So if I graph this and graph that, they should be mirror images of each other over that diagonal line, right? Okay, let's now get to logarithmic functions. So what we've been studying are exponential functions, right? 2 to the x, 5 to the x, 10 to the x, e to the x, 1/2 to the x, right? We know what the graphs of these look like, right? That is an example of exponential growth, right? So we know that the graph of this looks roughly something like this. Has a horizontal asymptote this way, it grows like that. We all know that the point 1, 0 is on that graph, right? So is that graph 1-to-1? Yes. It's a 1-to-1 function, isn't it? So it must have an inverse, right? It must have an inverse. I'm going to go a little bit further. To graph this function, to graph it, what you would do is plug in some points, right? Plug in some points and plot them. And I think I said, you know, we could plug in like a couple of negative values, a couple of positive values. Then you just plug them in. 2 to the negative 3, right, is 1/8. We've done this before, so I don't want to go into a lot of detail. 1/2, 1, 2, 4, and 8, right? That's what would happen if we plugged in those values. And we could plot the points and get that little growth, right? Is that all right? Okay, so now the question is, since this is 1-to-1, what is its inverse? What's the inverse of that function? Find the inverse. We know it exists because it's 1-to-1. So let's go through the steps. First thing you do, take this and replace the f of x with y, right? Yeah? Now, what? Everywhere you see y, put x. Wherever you see x, put y. Okay, x here equals 2 to the y. And the last step, solve for y, right? Solve for y. Solve for y. Oh, I have red, yeah. We're going to have blood tears here. These are tears of blood, okay? We can't solve for y. How do you solve for y? How do you get y out of the exponent? There's no way to do it, right? There's no algebraic way to do it. So we're stuck, okay? And this is what mathematicians were faced with. How do I get y out of here, right? And actually, we never really resolve that question. Like, we never really resolve how to get y out of the exponent. What we do instead is this. We say, whenever we see this expression, right? Whenever we see that, what we're going to do is create some new notation that is going to represent what this means, all right? So think about what this means. It means that x, right? This x value is what you get when you take this 2, right, and raise it to this power of y, right? Okay, so we have to come up with some new notation that represents this sort of relationship between the x and the y. And the notation that was chosen is this notation. What we will write is this, log, which stands for logarithm, all right? And then what we write is a subscript below the log of the number 2 here. So whatever the base is here becomes the subscript of the log. And then you put x here, and then you put equals y. So it looks like I've solved for y, right? It looks like I've solved for y, but all I've really done is come up with a new notation that means this, but is written this way. And when you do that, you actually see that you could say y has been solved for, right? So this right here becomes the inverse function. But it's truly just notation. That's all it is, notation. Some way of us representing that. So this right here, our inverse function, is this log with the little subscript 2 and then x. Okay, let me do it again. All right, but this time let's not use 2 to the x. Let's use a to the x. Just an arbitrary function. So let's do a to the x here. That's a generic exponential function, right? That's a generic one. And then we have some restrictions here. Remember, a has to be positive, a can't be 1, right? A can't be 1. Those are the restrictions we have for all exponential functions. Let's find the inverse. So if I go to find the inverse, right, the first thing I'm going to do is write down, switch the f of x to y. Now, everywhere I see y, I put x. Everywhere I see x, I put y. And now I solve for y. But I can't solve for y. So I use this new notation we have. So I will write down log, what's the base of this log, or what's the subscript here? A. And then right here I put x, and then here I put y. Now, students will often write this down. They'll be like, did I get it right? Did I do this correctly? And the way that I teach my students is a way to remember this is something that I call the loop, right? The loop. I've never seen a book talk about a loop. So if you go to a tutor and you're like, the loop, and they're like, what the hell are you talking about? Okay. The way I see it is if I want to make sure this is right, what I do is I draw a loop that goes from here to here to here. See that little loop? And what this should be is a raised to that should be equal to that. So a raised to the y should equal x. Is that what we have here? Is that what this equation says? A raised to the y equals x. Is that this? Yes. So I've written it correctly. Do you all see that little loopy thing? Okay, so let's write the final answer. What is the inverse of this function? Log with the subscript a, x. That is the inverse function, all right? So look, all a logarithm is at this point is just another way of writing something. That's all it is, just a notation to help us write something that we couldn't solve, right? That's it. But we need to go a little further than this because this is a function, right? This is a function. And when I graph this function, it should be the reflection of that one over the diagonal line, right? Shouldn't it? How in the hell am I going to graph this, right? How do I graph this? So let's do that. Let's get to that. So what I'd like to do, that right there is right now our general answer, right? If somebody gives you a function f of x equals a to the x, then the inverse of it is this thing right here. And the way we say this, okay, just so you know how we say this, this is called the log base A function. The log base A function. And that's what it says right there. Logarithmic function of base A. You can mix these words up. Okay, it's the log base A function or the logarithm function of base A. So this number right here is our base, isn't it? Isn't that the base of the exponential function as well? Okay, so whatever the base of the exponential function is becomes the base of the logarithmic function. So let's go about seeing how we would graph this, all right? So let's go back to a specific example that we had a second ago. F of x equals 2 to the x. We said we already know what that looks like, right? But I want to go back to the table that we made. That table that we made, I'm just going to put the answers here. Right, those are our answers, right? Think about what an inverse function does. Think about what an inverse function does. An inverse function undoes a function, doesn't it? Whatever the function does, the inverse reverses that, right? So if I wanted to now try and look at the inverse function, right? Log base 2 of x, that's the inverse of that one. What should the t-table of this one look like? I plug in an x, and then this spits out something, right? So shouldn't it take every one of these outputs and send them back to the inputs, right? Send them back to those inputs. So if I put 1/8 here, where does it get sent? -3. What does 1/4 get sent to? -2. What does 1/2 get sent to? -1, right? What does 1 get sent to? 0, right? Every number that's in the y coordinate, right, gets sent back to the x coordinate. So let's see, what would come next? What goes back to what now? 2 goes back to 1, 4 goes back to 2, and 8 goes back to 3, right? That's what happens. So these are points on my graph, x, y, right? The inverse function, it's reversed. This is my x, this is my y. Let's take a look at this. All right, I have a graph ready to go here. All right, there it is. Hopefully you can see that. Can you all see that all right? Yeah? Look at the red graph. I'm going to hover over 0, 1, right? That's on our graph right here. 0, 1 is one of the points. And then 1, 2, and then 2, 4, and then -2 was 1/4, and -2 is 1/4, -3 is 1/8. So the red one is 2 to the x. Now, if you reverse the x and y coordinates, right, flip them over, you get the blue graph. Right? All I've done is reverse these. Instead of 1, 2, I put 2, 1. Instead of 0, 1, I put 1, 0. Right? Flip them and you get this. And do y'all see it as a mirror image? Yes? It's a mirror image. Oh, across the diagonal. We call it the identity function. All right. Y'all still good? But we still have an open question here. We still have an open question. If this is a function, right? If this is a function right here, and I were to ask you right now, okay, take this logarithmic function and plug in 1/8, you can tell me what the answer is right now, can't you? What's the answer? 3. -3, right? -3, right? It's -3. How do you know that? Because of this, right? If I ask you, hey, what's log base 2 of 1/4, what will you tell me? -2, right? You're just looking at those values over there and seeing what the logarithm function does, right? But what about this question? What is log base 2 of 16? That's not on your table, is it? It's not on your table. However, without looking at this, we can still figure this out. Because what does this really mean? We want to know what this is, right? We want to know what this is. Think of the loop. Think of the loop right now. What is the loop saying? When I take 2 and raise it to some power, right? I need to get what? 16. Do you know what that power is? 4, right? It's 4, 2 to the 4th power. So you can answer this, can't you? You can say that the answer here is 4. Understand? What if I do this? What's log base 2 of 1/16? Well, now you need 2 to some power to be equal to 1/16. Yes? -4. So how are you doing that? Okay, so over here, you can look at this as 1/2 to the 4th, right? 16 is 2 to the 4th. And then bring it up and make it, let me come up here. This will be 2 to some power equals, I can rewrite that as 2 to the -4. And then now these two have to match, right? Which means your answer is -4. Y'all kind of getting this? Questions? You sure? I'm going to ask you another question right now. What would this be? So raise your hand. Don't just shout the answer, because I'll probably have the same people give me answers the whole time. Who wants to volunteer their answer? You got something? Okay, hold on. You got something? Hold on. You got something? Hold on. What is this really asking? Do y'all see the loop? Okay? So the loop is really saying to us what? 4 raised to what, right? You could say x if you wanted to, okay? You don't have to put a question mark. You don't want to put x? We can put a variable, that's fine. 4 raised to something, right, must be what? 16, which is 2. Okay? So the answer here is 2. So we actually can figure out the value of these things, can't we? So long as we know that loop, right? How about this one? Log base 4 of 15. So what's it asking? What's this really asking? 4 raised to the x, right? Must equal 15. We have problems, right? Don't we have problems? Because 15 is not a power of 4. And so you can't do what we just did over there, right? We can't just say, oh, 4 squared is 16. 4 to what power is 15? So we're stuck again, aren't we? But at least we know what this means now, right? This logarithm is really, if you look at a logarithm, what it's doing is it's saying, look at the base. Figure out what power you raise that to get that. That's what a logarithm is doing. That's the question it's asking. Are we clear? Does it make a little sense to you? Okay, I want to continue with my notes here.